o microfone ambiente?
Já estamos no ar.
Já estamos no ar?
Pode
Tá
falar.
bom. Obrigado.
Não.
Bom, então é grande prazer aqui que nós temos a presença do professor Fabrizio Granelli, que vai nos dar uma palestra hoje intitulada Digital Twin 6G from Theory to Practice. Fabrizio Granelli is a full professor at the Department of Information Engineering and Computer Science at the University of Trento. He received the laureate master's degree and PhD degree from the University of Genova in Italy in 1997 and 2001 respectively. He was visiting professor at the State University of Campinas, and in 2016 he was visiting professor at the University of Tokyo. He was a IEEE Consoc Distinction Lecturer for the period of 2012 and 2015, and 2021 to 2023. Consoc Director for Online Content from 2016 to 2017, Delegate for Education at University of Trento in 2015-2017, IEEE Consoc Director for Educational Service 2018-19, and IEEE Consoc Director for Conference Development from 2022 to 23. Professor Granelli was the General Chair or TPC Chair of several prestigious IEEE conferences, such as IEEE Globecom, IEEE NFV STN, IEEE CAMAD, and chaired several symposia at IEEE ICC and Globecom. He is the founding chair of the Aerial Communication Emerging Technology Initiative of the IEEE Consoc and chair of the IEEE P1954 Standard Working Group. He is the author or co-author of more than 250 papers and published in international journals, books, and conferences. He was Associate Editor-in-Chief of the IEEE Communication Surveys and Tutorials from 2017 to 2022, and Senior Editor of the Transaction Green Communication Network. It's a great pleasure to have Professor Fabrizio Granelli delivering this talk at the Institute of Computing. Thank you, Fabrizio.
Thank you, Nelson, for the introduction. Thank you all for coming. It's a pleasure always to be here and present what I believe might be interesting, which is a topic that basically involves two things that I like. One is traditionally mobile networks that is more than 20 years that I'm facing those problems, as well as the self-adaptiveness, let's say intelligence, cognitivity in networks, which is another of the topics that I prefer. So with the topic that I will present today, those two topics come together in a nice way, and I think now it's a time when the technology is mature for bringing them together. Before it was more maybe looking too much in the future. So that is why I entitled From Theory to Practice, because I will first speak about digital twins. Digital twins is a topic that it appears in a lot of works, in a lot of sectors. In some it is very practical. In some, like networking, it is mostly theoretical. So I will try to tell you which are the lessons that I learned by trying to make digital twins real in mobile networks. I don't know, it's... I mean, I can go with the keys, but... Okay, thank you. So first of all, this slide is a little small, but if you are not familiar with the concept of digital twin, the digital twin is the digital replica of something that exists in reality, that is called the physical twin. So we take an object, a device, a process, and we transform it in a digital version. What is different from a simulation, for example, or from any other traditional technology is that the digital twin should be always in sync with the physical twin. So when we build something that is the real digital twin, should represent exactly the original twin, the physical one, but also the state of the physical twin. So if we build a digital twin of a car and the car is moving, our digital twin should reflect this state. So it should have wheels turning and maybe braking, maybe other kind of sensorial exchange between the real world and the digital one. So why do we use digital twin? Digital twin is a very mature topic already in manufacturing, for example, and in general, let's say in IoT, because it is very useful for studying the state of the systems without requiring inspection, direct inspection, and to predict, for example, maintenance. There are a lot of examples already in production of digital twins that are used to study, for example, when an airplane or another complex device requires maintenance before something breaks, for example, because there are already some, let's say, preliminary measurements for the sensor that can predict that this will happen in a short time. So the power of the digital twin is that it's like a toy that we have. We can play with that. We can perform measurements, simulate what-if scenarios, so we can check what would happen if something in the state changes, without affecting the physical twin directly. So we can, for example, take decisions on what to do on the physical twin, but trying which are the best solutions without any impact on the real twin. So just to briefly remind, it's a when we want to build a digital twin, we need a physical entity in reality, in the real space. We need to transform it in a software version, and we need to have a communication link, hopefully bidirectional, between the two that allows to sync the state, so that we have a real situation in our digital format. What makes it interesting from the network and communication perspective is by itself already the fact that there is a communication between the real world and, say, the digital world, because we need to keep this communication alive, because we want our digital twin to represent also how the system in reality is evolving or what's happening in the context of the system. So that is a specific thing that must be underlined, because otherwise anything softwareized would seem to be a digital twin. It's not exactly like this. We want something that represents the real state of the system. And when we look at how to use the digital twin, there are different approaches. This, I think, it's quite a useful sort of environment to describe it. So we start from the real space. In the real space, for example, we can build digital twins of renewable sources, of 5G, 6G, or even applications. Whatever it exists, we can generate a digital twin version. Of course, there is this is the connection that keeps the state synchronized between the digital and the physical twin. And then what do we do with the digital twin? Once we go in the digital world, what we build typically is we build a sandbox or some virtual environment where we can use one or more digital twin, where we can host the digital twin, and then to implement algorithms or methodologies on top of that. For example, there is the digital service layer, where you can have predictions. I can check what happens if my system breaks one component, for example, or if something from the outside happens. We can do integration of different digital twins, so we can build a more complex structure by combining different digital twins. And also, that will be very interesting for networking. For example, you can use the digital twin for training machine learning technologies or artificial intelligence technologies, avoiding to use the real version, because sometimes we don't have access to the physical version, or we cannot, in reality, build a situation that we would like to study, because maybe it's dangerous. Like we want to understand what happens in an emergency situation. To do it in reality is complicated. There we are in the digital world. We can do what we want, so we can perform also training operations. So we'll come back to that in a minute. So when I found this concept, I thought that it was interesting to think how to deploy this technology in networking. And also, I will try also to explain you why it might be useful to have it. So in networking today, we have some big trends that are sort of crossing the different topics that are related especially to the softwareization, because there is a lot of approaches that detach software from the hardware so that the software can be used and reconfigured more easily, and this allows the network to become more flexible. And this leads to automation, because networks are supposed to become more and more automated because of their complexity, because we are increasing a lot of complexity, even with softwareization. So on the other side, we want to have networks that will work better than before. So we need the networks to be sort of self-managing themselves, maybe 100%, maybe less, but at least to contribute to the management. Then, as I mentioned, there is a lot of enthusiasm in today applying artificial intelligence everywhere. In networks, of course, is another topic where it fits very well. And last but not least, there is always the problem of sustainability. So to have the capability to develop networks that are sustainable from, for example, the energy consumption point of view, pollution, and so on. So there are those topics that are transversal, and they are sort of combining themselves. The digital twinning is a strategy that can help in some of the subjects that I presented before, because if we look in the modern networks, we will need to have self-awareness, so to be capable of managing a lot of data and understanding the state of the system with quite a high level of accuracy. We want the capability of prediction, especially, so we want to understand and predict if something is going to happen in the network, because we want to react as soon as possible or even avoid problems. And there are also other problems that are the capability of handling heterogeneity, because the more we softwareize also, the more the system becomes heterogeneous actually, because we can run services on any kind of hardware today, we can distribute them and split them. So we are starting to have a very large distance between the service and the hardware. So it's difficult, for example, to understand how to reduce power consumption, because we are not aware about what happens below our virtualization layers. And also, that is very important, we want to be able to analyze what-if scenarios. So we would like to, let's say, have the capability to implement some maybe futuristic situations to be able to understand how to handle it before they happen. So we want to see, to make hypotheses and be sure that we are ready with our technology. And on all these topics, we can apply also the idea of digital twins. And I think digital twin really is a way to implement those technology much better. Then I was also mentioning digital twin in 6G, so I will restrict a little bit today the application to mobile networks, even though a lot of the things that I will say are quite general, because in 6G there is this ecosystem where you have, it's already practically clear that the difference between 5G and 6G will be almost the presence of more intelligence in the system. So you see on the top, this is a general structure or ecosystem. You see there is a lot of learning, self-generation, checking of strategies. that are going to be almost automated, maybe sometimes also with the human in the loop, but here they already imply the fact that when we want to analyze and optimize a scenario, we will for sure have some sort of digital twins. Maybe not of the network, but they could be digital, that 6G will enable to have digital twins of other systems too. So there is already, let's say, the impression that to have an efficient 6G, we will need to have somehow artificial intelligence in the loop, and I will show you that artificial intelligence will require on the other side also digital twinning. This is an example, very high level, of some thoughts that we had 5-6 years ago when we were discussing with some colleagues about this idea. So we believe that the digital twin can fit very well in the closed loop of network management, because today we have basically in 5G a network infrastructure. We have slices because from 5G on we expect that the network will be split and isolated in different ways, and we also have, for example, services in the simplest example. Already this makes the system extremely complicated, because we have to understand, for example, how to give resources to the slices to perform or to fulfill our objectives. What are the requirements of the services? You know, now they speak about intent-based interfaces or predict also how the service will behave. And also we have to be sure that the slices will satisfy some constraints, or they might be modified depending on the traffic that runs in. So our idea was that we can build digital twins of the network. Even we can build a digital twin of what happens in the slice and of the services, because they are sort of different domains somehow. And we are combined together in this digital twin sandbox so that our system can run machine learning, for example, to optimize the overall resource utilization, to minimize power, or to do other stuff, or maybe just to check what happens, whether, for example, we can accept a new service or not. There is a new service incoming. Let's decide whether we can maintain the quality of service of the others. This is a question that we can address. And of course, that is what closes the loop. So the network manager will always decide on its own. So you can apply policies and decide whether the decisions that are taken through the digital twin are realistic or not, but still you will have a lot of more information to take an informed decision. Here are a few examples that we made within my group. This is a very simple concept, but still already not trivial. We took one network, it's an SDN network, very simple, just 5 switches and a few hosts. And our objective was simply to understand how to allocate the traffic, how to engineer the traffic in order to reduce the energy consumption. So what we did is we built a method that automatically transforms the physical twin, that in our case was this network, into a digital representation. For example, that is what this sort of intermediate diagram shows. And finally, we decided how we wanted to represent and what we wanted to represent of the digital twin. So you see there, what we decided to model was the power consumption of the chassis of the switches, because you know there is fixed power consumption, and the other component of power consumption is the ports of the switches, because depending on the bit rate they have different power consumption. So we built automatically, so changing the physical twin, we could change automatically that one. That is the topology of our digital twin, which was based on very simple but taken from the data sheets, the power models. So what we did basically was to have a sort of first example of digital twinning by exploiting the SDN controller, because basically we exploited the fact that the controller, that here is you, can get all the information that we require from the network, the topology, the traffic state, and so on, and we can use that to build our digital twin on the top there, so that then we could play with the digital twin. And in our example, what we did is we implemented a very simple algorithm that was getting information to build a digital twin, and then it was running different routing strategies to understand whether we could reduce the number of active switches and the number of active ports, so that at the end, what we get out of this reasoning loop is the solution that minimizes power without any loss, just rerouting traffic and turning off what we don't need. And in this way, you see that is let's say the graphical representation of the routing that is selected. Knowing how much power per interface we were using, we found that, for example, the other comparison with fixing the bit rate to an intermediate level of the links or doing other choices, our solution, it's the blue, basically. So we were showing that in this way we could remain very near to the base power, so to reduce to the minimum the number of active ports, while maintaining the same quality of service and the same kind of level of service for the overall network. And this was done simply with very, let's say, simple and non-sophisticated algorithms, just to see what we could achieve. And the important thing is that you have, with the digital twin here, you achieve a very high level of awareness of the situation. So you can take very well informed decisions, because you know everything basically about the network. One thing was how you represent the digital twin. And for this, we have one software that we use also for teaching, that is a sort of an evolution of Mininet, where we can deploy SDN as well as also Docker containers. So this is an environment that we are using now for building our experiments in machine learning and so on, but also building the digital twin, because it's a simple environment, but it's an emulation tool. So we can use the real traffic, replicate it in the twin, and also run real services if we want. So we can have a very realistic vision of what's going on. Another example about using a digital twin is the mobile edge computing. That is one problem that it will arise very soon, because there is a lot of optimism about using the edge to deliver services, and of course it makes sense for a lot of reasons. However, it is likely that a lot of care should be taken in understanding which is the impact in the power consumption, because the edge is considered to be extremely diffused, because the idea is to have edge nodes very near to the users. So there will be multiple edge nodes, not as much as base stations, but maybe a subset of that. And those needs to have power, to have resources, and to have communication capabilities. So we found the edge very interesting from the point of view of heterogeneity that they represent, because different providers can deploy different edge strategies, different hardware, different virtualization solutions. So it's very difficult to have a single rule to decide how to make the edge energy efficient or how to orchestrate services on the edge. Because we need to have dedicated hardware somewhere, but on the other side, we might have scarce power availability. And also, the edge will be characterized by the fact that it will suffer from extremely variable load, because the edge exists to support local end systems. And of course, the end system can move around very easily. So we cannot have a fixed kind of orchestration strategy. We need to be flexible and optimize the power in order not to consume always a big amount where there is no, for example, subscribers. Here I try to explain better why edge is challenging, because we expect that there will be a lot of hardware and software solutions, maybe compatible but different. from point of view of efficiency. We have several virtualization layers because most likely it seems that the edge will be based on containerization, but maybe someone could put virtual machines or other stuff. So you can have different architecture for virtualization. However, the point is when you speak about energy consumption, the energy consumption happens in the hardware. The software, in principle, is virtual, so it's difficult to say one line of code how much power we consume because of all these virtualization layers, the fact that one CPU consumes power in a different way from another. So we need anyway to have some information if we want to optimize the consumption and to make the system sustainable. And or at least if you want for understanding the trade-offs. So I want to see how can I use my power for achieving the best possible performance and maybe maintaining a reasonable power consumption. For this, we built, this is one of the problems of digital twins applying to network, because the edge does not exist, at least not in the most, let's say, evolved way, because there are things that are on paper. So how can I build a digital twin of something that does not exist? It's an exercise that we have to do via virtualization itself. So what we did is we assumed that somehow we simplified our problem in this way, assuming that there will be the RAN part of the network, which is the first block. Somewhere there will be like a switch that will allow us to redirect traffic to the MAC. And then farther away we will have the core or the cloud and the core of the mobile network. So here we tried to derive from paper what could be a digital twin potentially for a real Mac node. And in order to do this, what we needed was to constrain the resources, because if we say that the edge node is limited in power, we exploited, in this case, our emulation framework with Docker containers to understand how to restrict the amount of CPU allocated to each node to represent a really constrained system. Here there are a few graphs to show that we could emulate, for example, one or more Raspberry Pis, making some experiments in order to understand how to assign the CPU of the emulator. Then what we did was to verify that there are trade-offs, because if we can get the best throughput, the lowest power consumption, and so on, there is no need to make much investigations. Here there are a few graphs, but the important one is this one, where we were showing that because in Edge, most likely, even the switching part will be virtualized, there is a trade-off between the throughput that you can achieve and the computational load that you can have on the Mac node. Because if you charge too much the Edge node, for example, if you have too much computation because you run machine learning extensively, or you run very computational intensive strategies, then you reduce the capability, because the CPU is the same, you reduce the capability of the CPU to switch traffic, because one of the components of the Mac will be probably the user plane function that somehow will be allocated in the same place. So this diagram shows that depending on the power that you have, if you have more power, if you have more power on the edge, you can achieve a reasonably higher throughput without impacting too much on the amount of computational power. But if you have very scarce resources, the red, you are bandwidth limited because the CPU cannot go around. So this means that we need to be careful in also how we softwareize the system, because if you put too much stuff on the edge, maybe we self-constrain our performance. And basically what we found is that depending on the resources that we give, there are different, let's say, achievable regions. Probably the more interesting conclusion is this one, that shows you that there is a combination of CPU usage that you give to one application and CPU usage that you give, for example, to the user plane function, that provides some non-achievable configuration. So I cannot have very high switching power and very high computational power, because you have to reallocate them in order to balance this. And the points represent some reasonable operating points. This is important because in this case you can have real services. We made these simulations, these emulations with real services, some just more computational intensive, some more communication intensive. So we believe that this is quite a realistic vision of the trade-off here between computing and communication performance. Then we added power consumption also. So how do we model power consumption? This is more tricky because we didn't want to have a very trivial model. So what we did, we built a lab test bed with some power measurement plugs, and we implemented different approaches to Mac node virtualization. For example, bare metal, virtual machines, containers, and so on. So we had different machines, and what we did is we made the same experiments as before, but this time we were measuring the energy consumption depending on the communication and the computational load. So we added a third dimension somehow to our performance. What we found out is that, probably you see visually, depending on the virtualization strategy that you use, only that, you change the behavior of the system. Because, for example, virtual machines are typically providing a higher overhead, so you don't achieve the highest performance, but still you consume a lot, because when you reach the maximum level, you are limited in the data rate that you can achieve, for example. The more efficient are bare metal and containers, but here the idea was not to decide between these three, but to show you that it's possible to derive this information, so that ideally, if we knew a priori what is our hardware working in this case, which is the behavior of our hardware, we could optimize the system. Because now, for example, if I know that I use containers, I can use the 3D curve in the middle and use it for orchestration. I can try to orchestrate my services, considering how much CPU and data rate I will need. I will find which is the optimal point that I can use. However, sometimes I don't know a priori what is the hardware like, because if you are a developer of a mobile application, probably you will not know what is in the edge. They will just tell you, you can put a container there. So how can I optimize my system, or can the network optimize the power consumption without knowing which is this? The other point is that we are studying right now is, can we build the same curves but in real time? So if we have your system running, can we build a digital twin while the system is running? So can we build those surfaces directly runtime, collecting data continuously from the network? And the answer is, of course, yes and no, in the sense that we can do it, but of course there will be some different levels of accuracy, because in this case we will have some holes. You see, these diagrams seem to be more smooth than before. These are different iterations of a machine learning approach to try to approximate the real curve, because you have holes in the measurements. You have less samples, so to build your digital twin, you also require machine learning, because machine learning will help you to interpolate the points that you don't know. So it will make reasonable assumptions, hopefully, about what happens in situations that still did not happen. But we can do it continuously. So this approach shows that you can build your digital twin incrementally. Okay, even if you don't have a lab to build the system, you can use sensors in a real system, not having any, let's say, interaction with that, but just capturing data while it's working to populate this information that is necessary then to optimize the system for the other level of machine learning processes. So the final picture, I mean, the full picture of this approach looks like this, basically. So you have your physical twin, for example, the physical twin of your Mac node, so the hardware that you put on the edge. Then what you do is you measure some KPIs and some parameters from the physical twin, like the current power consumption, the current load of CPU, networking, other aspects. Then you give these you use this for incrementally building your digital twin. This is GNN digital twin because it's a digital twin that is built via machine learning. So there is a machine learning process that continuously refines your model of the digital twin and updates the digital twin. Then, to optimize the power consumption, what happens is we will have some policies for service placement that will make experiments using the digital twin. So we will have a process that is this closed loop that will try different strategies and check what comes out as a prediction from the digital twin. So that when we reached our goal or we found the minimum, we can then define the action on the physical twin. So this diagram shows you a little bit the overall picture, where you have the physical twin that you use for capturing the data. Then there is a learning loop or a decision loop that works in the digital domain only. When you are satisfied about your decision, because the digital twin will tell you that it's a good configuration, then and only then you can operate on the real system, okay? With the advantage that this can be done at any speed. If you have a lot of computational power in the cloud, for example, because this part typically will be in the cloud, you can make it very fast, okay? Not maintaining the time of, let's say, the real-time clock of the system, because that happens in the digital dimension. So I can do it very fast, take a decision, but only take an action that I'm sure or I'm confident it will have good results. Here there is an example. This was very simple and preliminary work that we are doing yet. There is a diagram where we studied the problem of orchestrating different Mac nodes with different hosts and different services. And what we tried to do was to sort of load balance the nodes. So when possible, to define different nodes to serve different users and to allocate different services in order to maintain the same quality of service. So where basically the stars that you see in the diagrams are using different strategies when the digital twin predicts that there will be a negative feedback on the quality of service. So when there is the star, it means that the choice that is taken at that time in the virtual world is wrong, because it didn't satisfy all the quality of service requirements. So what we did is we made some simple algorithms to try different choices, even random, but multiple. So we gave the digital twin different random allocations, and we asked the digital twin which was the best, the one satisfying QoS and reducing power. And at the end, what we found out is that this is the optimal allocation, that is NPR, but in this case it was a small testbed. So we can see that the QoS, basically, this is random, but using the digital twin, this is just random, so allocating randomly the tasks. You see that you can satisfy basically all the quality of service requirement of all flows, with the advantage that you basically reduce the power consumption by 30%, okay? And this is a very simple approach, because of course not all the time the digital twin will be correct. I mean, there will be some approximations. Sometimes, if you see there is a little, here is not exactly 100%, there is some discrepancy because the accuracy is not the best. We are still working to make it better, but it shows the potential benefits of using a digital twin. So just to close a little bit and try to wrap up, what are we doing now to move forward? To move forward, what we are trying to do is really to try to unleash the full power of digital twins in 6G systems. And we believe that the two interesting points will be this one. One will be to train. to train machine learning and artificial intelligence. This is because we did some previous work also with Nelson about cognitive networking or networks that can self-optimize themselves. But the main problem was that you cannot, in reality, make experiments in a network that is in production. So no operator will accept to have a network that can fail at the beginning, so to learn, because this process does not, of course, satisfy users and so on. With a digital twin, this is completely avoided because we can train our systems on the digital replica of the system, of the real infrastructure, and only take actions that we believe are realistic. Of course, we might still have accuracy problems, but this will help a lot in having a more refined learning process. On the other side, the other thing is, especially for security, it's important to perform modeling and prediction, so to understand, again, for example, where power goes, or to predict if there is a security breach, or what would happen if someone would use a specific strategy, because that would help to make reliability higher and also security higher. So here is a quite complex scheme because we have, I'm coordinating a European project that is called ORS on this specifically. So it's a 7 million project on, let's say, giving feedback for standardization, because ECG standardization is still starting. So the idea of this kind of project is to explore some new scenarios. And here is how the digital twin fits. It is this block. So basically what we do in this project is the infrastructure is below. Everything here is in the software world. So from the infrastructure, we collect data, and we use the data to build the digital twins in this sandbox. That is the yellow part. Then we have, this is a lot focused also on security. So we have some modules for detecting and mitigating security breaches, for example. And we also have the intent-based interface to understand what services and users would like to do. So basically what happens is, if, for example, before taking a decision, which is on top there, that we have an AI engine that will suggest to the network manager some decisions. What happens is that, for example, the intent-based interface can predict a request for a service or an incoming problem. It will check with the digital twins that we have two, but we can have even more. So the digital twins will run potential scenarios, and then will give advice to the recommender. So we will use the digital twin to test strategies or to predict what is happening, if for example, in the next hour in the system, so that every management decision will be taken, of course, modulated by the policies, because we cannot do everything that we want, in an informed way. So what we will try to do, we will try to demonstrate this closed loop, that of course it's not easy maybe to describe, because there are a lot of implications, but the core here will be the digital twin as the tool for providing context awareness somehow, and also predictive capabilities. So that is what, this we just started, so we are just implementing first ideas. Maybe next time I will tell you how we are doing with this. Here is just to show you, because I said from theory to practice. So in practice, how it will be the digital twin in this case. This is a zoom of one digital twin, the one that I'm responsible for, which is prediction and prevention. How we are going to build it? We are building like this. So we will have a modeling module that will take the data, maybe with machine learning, maybe with simpler strategies. It will build the digital twin automatically, so without any pre-configuration. So it will detect topology and so on, traffic flows, and it will model also traffic flows to make predictions. Then this will be used to drive the digital twin engine that can have multiple instances, because maybe I run 2 instances of the same twin to compare them, because in one I do one choice, in another another. Then this will be used to perform prediction, because I might want to look forward, like what happens in 2 hours from an attack, for example. And this will interact, of course, with the other blocks. Or directly, the digital twin engine will be accessible from the other blocks just to perform experiments. So I can say, okay, what happens if this module, this network function is put in another place? I can tell you, I can run the digital twin and say, you get maybe smaller delay, so that will be best. So that is an example of how maybe digital twins will appear. We are implementing currently those modules. That is how you can integrate the real context, but also models, because the thing is, today we don't have 6G. So we can use 5G as our baseline, but for example, in the digital twin, we could have this arrow saying that maybe we have a new functionality that does not exist, but we want to see what happens if we would have also that one, okay? Maybe in 6G we have some new modulation or some new RAN technology, we can model it somehow. Of course, that will not be synchronized with the real twin, but we can also, it's a what-if, scenario to test. Last point, actually research is progressing quite fast on digital twin. I just mentioned, for those that are interested, there are probably two most important groups at the moment are the ETSI Experiential Networked Intelligence, ENI working group that is working on how to integrate basically intelligence in 6G. So here there are a few references if you want to check the white papers or some short description. But also the Internet Research Task Force, there is a working group on digital twin of networks. They call it in this way, digital twin network. And that is just a snapshot. They came out just April this year with a first specification of very high level specification of what the digital twin would look like. And you see, it resembles what I presented you. So you have your real network, here you have data collection and control, because when you take a decision, you can, of course, control the physical twin. Then you have your instance of the digital twin, that, of course, here they also foresee a management framework for digital twins. And then finally, you have the applications to run on top. So, for example, prediction would be one application that you run on top. Then, or the intent, for example, you say, I would like to do that, the digital twin will work and maybe take feedback there. So it is a topic that is going to come in reality probably relatively fast. To conclude, I presented a lot of stuff. I hope that I conveyed my sort of enthusiasm, if you want, for this topic, because I think that it's a new topic that will find a lot of applications, and especially in the next generation of mobile networks. This is because 5G already introduced authorization and automation and potential, let's say, automation. So 6G probably is going to close the loop. So to put also the intelligence that in 5G is implied, but it's not in the standard. So I believe results are promising. What I presented you are very preliminary results. I think we can do much better. And I think it's a good topic for research for sure, but also in standardization, because the 6G will become real in 2030 roughly. So there is still some years to impact on the standardization. If you want a little bit more of information, you can check out the website of our project that now contains just some preliminary stuff, but in the next months we will come out with more details, because we are working on implementing the architecture now, so we will start specifying interfaces and so on, so it will be interesting to check our update. And here there are some works that we published recently on digital twin. Of course, we have more in preparation, but some of the results that I presented were presented at NetSoft this year, or they are available in networking letters. So if you are interested, please take a look there, or maybe just contact me. So with this, I conclude my speech, and I hope you liked it, and I'm available for questions. Thank you. I think I...
Questions for Professor Fabrizio Granelli, digital twin?
I have one question about how to understand the digital twin in a production situation. For example, you should always be always be up to date with the production system. Otherwise, once you're testing digital twin, you are going to provide the reality.
Okay, I think I understood. So,
ask you to repeat so people can hear.
okay. Yeah.
So basically, how to maintain the digital twin up to date with reality, the production system. So what you do in the digital twin maintain the reality.
Yeah, that is actually one of the challenges. There is not a single solution. For example, what we believe might be appropriate, it depends on the processes that build your digital twin. Because, for example, in a network, what we believe is that we can have, let's say, periodic snapshots of the network, because typically we will not be interested in what happens between one packet and the other, but mostly, to predict how flow will evolve. So in a network, the way we will keep the digital twin synchronized will be to ask, for example, to the SDN controller or to some database data periodically, maybe every 10 seconds. I'm just saying a random number, okay? But that is one thing. Another thing is when you play in the sandbox, of course, you need to freeze the snapshot, because I keep my digital twin synchronized, but when there is a request for an intent, for example, I want to see what happens if someone will do a denial of service, then of course my digital twin will differ from now on from the physical, because I will start predicting. Okay, so I will have a version of the digital twin that remains synchronized for reference, but the experiment will be run separately. Okay, that is the reason of the sandbox, because you can cut out. Let's say you take a picture, then you run the prediction, you see what happens, then you get back to really synchronizing, okay, in that case. In case, instead of digital twins of different objects, like if you build a digital twin of a drone, for example, that is other things that we are doing, in a drone you need a very much more frequent sampling, because in the drone you want to understand whether the motor is spinning correctly, so there you will need much more data. Okay, we don't have yet the numbers, but it's a problem of sampling. So you can know in the processes, you need to understand how much frequently you need the data. And there probably you might need compression or more machine learning to make it possible, because to transfer gigabytes of traffic, it can be challenging. Okay, it's a good point. Yeah. There is no rule, but there are some, let's say, background laws. Thank you.
Questions?
Thank you for talk. You're talking mostly about like independent digital twins. So I have a single digital twin. How about maybe standardization efforts or something like that for digital twins communications? Like you have to couple the digital twins or multiple digital twins to communicate to each other, so they can understand where they sit in the whole environment. How does this work, or do you have anything like that?
Very tough question. We already started thinking, but the reason at the moment we started with one digital twin because it's complex enough. But yes, I think that also there is where we will see even more potential. The problems are multiple. One of the main problems is that, also connected to the previous question, probably different digital twins will live in different time scales. Because, for example, if you have, an example that we had in mind was, we want to study power consumption. So let's build a model of renewable sources, for example. So the generation of a solar panel. There are models, so you can build it. But in solar power, typically you have a very slow, with respect to the network, a very slow variation, because solar cells are quite stable. So maybe you need to sample once every minute, which is already a lot. So you will have a digital twin that operates, for example, in minutes, and maybe the network that operates, that is synchronized every second. So the communication problem will happen also. We need to be studied in such a way that you can sort of run a common clock. So it will be not trivial. Of course, we will need to study a way to find, an alignment between the two, because otherwise, you can also have, depending on the way you compose, you can also have maybe not a direct link, but like an asynchronous link. Like in IoT, you put data and you read. For example, the digital twin of the solar panel could put the current power evaluation in a database, and then the other digital twin goes just to pick up how much power you have. But this is a very important point that needs further investigation. Because yes, the thing should be then to build bigger digital twins by combining the others. Because if every time you build a new digital twin, it's a waste also power, computation, and so on. No, I don't have references on that. It's very futuristic.
Questions? Fabrizio, so we have these examples that you mentioned, the power consumption, and also that the physical and the virtual should be integrated through communication channel. But there is obviously a time scale that actions from the digital can affect the physical.
Yeah.
So you kind of mentioned that like orchestration or moving from max to the other, it happens in time scale, but there will always be the limitation of smaller scale to take action from the digital to the real. Right?
Yes. Yes, this will depend how you fit the digital twin in the control loop, because you can have, in principle, let me show you. I know that this is a complex structure, but we decided to have this structure because we can address different time scales, because in principle you have the data here in these two modules. The network offers the data for building the digital twin, so you get some stuff, and here you build the system, let's say, synchronized to the time of freshness of the information that you have here. When you are here, actually you can run different time scales. It depends on the rest of the system, because if you want to take even very fast decisions, you can do it with the digital twin, because this can run at arbitrary speed. You can speed. It's like the clock here is virtual, okay? So typically we assume that we reflect the real clock, but no one tells that we can accelerate the clock. So you can run faster things, even for, I don't know, say in 1 minute what will happen. Of course, it depends on the rest of the system if it's capable of keeping up, because you give them a lot of information they have to process, understand, because that is necessary. They have to check it against the policies, because otherwise, there is this fear of the rogue AI. So to have AI that will control everything, this might happen, but there is this policy and compliance assessment. So here we have a lot of blocks that supervise that the decisions taken through the digital twin are still, let's say, affordable. because otherwise, and that is probably the constraint on your time, because if that block should be able to very fast understand whether the decision impacts or not in the policy to allow to go down. Okay, so the rest I think you can go at arbitrary speed, of course, maybe not packet by packet, but let's say that maybe in I don't know, in 5G, typically, for example, scheduling in the run, it happens every 10 milliseconds in the overall. This I think is feasible. You could have some digital twin that operates faster than this. But it's a matter also, it will have what we are not doing here, it will have a cost, because maybe to run this emulation in a data center will cost a lot of money, because I need a lot of resources, because the faster I go, the more I will spend resources. So I think that the solutions will be more constrained by how much resources you are going to have for your digital twin, and whether you need it actually, no?
If you can react at the millisecond scale, that's
yeah, that would be great, but probably I think those are things that maybe you can, for example, to work like millisecond speed, probably you need to make, you can do it with this architecture. You might have the intent-based interface giving you some parallel decisions, because in general one decision probably will be okay for a long time. I mean, maybe not, it will not change every packet. So you might have already scenarios, so use the digital twin only to have different pictures and just tell the network manager to select one. Because you can say, okay, let's emulate what happens if I don't know, I reroute traffic or I move the network function. The digital twin will give you 3-4 performance results, and then every time you must take a similar decision, you don't need maybe the digital twin that say, okay, I learned that it's like this. So that you can do faster, because you can, that is in fact, by the way, it's how you train the AI. Because if you train the AI, then the digital twin can be detached. I mean, once the AI is ready, if there are no changes in the network, AI can take its own decision. It's only a consultancy, let's say. It can tell, okay, I'm not sure, let's see what happens in the digital twin. It goes like this, then it learns that this is best. So there is a lot of closed loops here that needs to be actually studied.
Thank you. Any other question?
Here, I think you discussed about the service placement in the previous slides. What criteria you used for the service placement? And also, my question is, when we have a digital twin migration problem of a digital twin migration from one base station to another base station, then how we can mitigate this problem of the migration of digital twin and also the service migrations? How we migrate the services of this digital twin to, because he is migrating to next base station.
Okay. Actually, what we assume here is that all or most of these modules will be in the cloud. Okay. This will be the module that will interact with the infrastructure. So you have the RAN, the core here, but the rest is, or here also you have the infrastructure. But the rest will be in the cloud. So basically, you will not migrate the digital twin itself. This will be another aspect, but typically it's not too much addressed at the moment, because we assume that the digital twins are in the cloud. Okay, so we don't study because this will be another issue, how to migrate the digital twin in another position. It would require, of course, to reroute all the sensor data or the perceived data in another place. But at the moment it's not the problem, because even with the Mac, the idea is that the digital twin is not in the Mac. I mean, if you build the digital twin of the Mac, it is still in the cloud. So everything is assumed to be in a data center, basically. So you migrate only between one workstation and the other in the same rack, or so you don't have problems of bandwidth or things like that. But it might happen in the future if the digital twin would be nearer to the physical twin. Maybe that can be, but it will be and another team more advanced to study. But of course, might be a problem.
If this will happen with physical twin, then
If it happens with the physical twin, it's a problem of reconfiguring more than migrating. So what will happen if, for example, in my network I build the digital twin of the users, because I might need the digital twin of the users to know the habits, for example, so to predict how they will move or what they will do. If there is a movement of the people, I can just update, let's say, the topology, the virtual topology that I have here. In fact, here in this project, we will not do it very real time because it's already complicated to take on all the system. But in principle, you should get updates from this module if there are changes also in the network, because you can choose. Probably what will happen is you build your digital twin once, and then you just get the news, let's say, so the new sensor information, the new state information, and the changes. For example, one switch went down, let's say, then you synchronize the twin. So this would be, it would be done, maybe not real time, but probably with like an interrupt, sort of interrupt to the digital twin.
First of all, thanks for the presentation. My question is the following. As you mentioned, it's very difficult that you must test your digital twin in a real scenario because it would be costly and I mean the network can't stop. So what are the considerations that you have in order to make a good digital twin model? I mean, a good model. How do you model these digital twins? What considerations do you have? Because if you test different scenarios, they won't reflect the reality. So how
Yes.
do you do that?
Yeah, it's an important question. I think that the way you build your
And how do you validate that it really will work there? Do you
Yeah.
have any metric to validate that?
That is also interesting. Let me first answer. The first point is I think that there will not be a single way to build a digital twin, but it will depend on the purpose that you have. For example, I presented before, since here it was a very preliminary work, but here we didn't want to study anything other than just find a way to reduce the power. So we didn't need all the details, but we just needed the links, the topology, let's say, and the corresponding power consumption. So we used models, for example, for the power consumption taken from the data sheet. We took, those are, let's say, you have them. But of course, we didn't arrive to the maximum level of accuracy, but for this problem, it was enough. So it depends because to build the digital twin is similar to building the physical twin. So it's a combination of objects. So for example, what we assume in the project is that we will replicate all the objects that are the 6G. So we'll have switches, we will have the core network, the service-based architecture modules, we will have the RAN. So this is one way to approach the problem. So knowing that you have these building blocks and then just configuring them depending on your knowledge. But instead, another way to do it, if you only need maybe to take some informed decision, can be the one that we used here, which was to make measurements in the lab and build a response surface. This is a mathematical, let's say, digital twin. It's still a digital twin because it will provide me the information that I need here. So the answer is it depends the purpose that you are building the digital twin for, because maybe sometimes your network can be a black box only with input and output because you just want to simply understand let's say the delay, and you have a model, so you can build it like this. this leads to your second question, that is how you evaluate the accuracy. It's difficult to say. What I think is what you can do is to compare the outcomes. For example, in the last this one, let's assume that there is really, for example, the system predicts that there is a denial of service attack, so it's happening. Then the AI engine might ask, what happens if I turn off this switch, I don't know, or I change a firewall rule, okay? The digital twin will make the computation and will say, okay, this way you block the denial of service. Then the artificial intelligence will decide to do that. It will learn that, but there is another feedback loop that is here, you see it's the one on the top. There is another feedback loop that will be the consequence of the action. So first of all, I learned from the digital twin that this was a reasonable solution. When I take the action, the artificial intelligence module will check in reality whether the denial of service was stopped. And it will learn if the digital twin was accurate or not. Okay, of course, there can be, again, some accuracy problems, in the sense that the decision was wrong, but the artificial intelligence will learn, and next time probably it will maybe give lower weight to that decision, or it will learn maybe to ask another question to the digital twin. So for sure, digital twins will not solve completely the problem of wrong actions, but they will be part of a learning process that should be more controlled, because artificial intelligence will be able to train both on the real data. If you have historic data, for example, you can train it anyway, but also it will be trained on the perspectives given by the digital twin, but it will also learn from the real decisions that are then taken. So we will have, let's say, at least 2 levels of refinement of our decision. Again, I agree with you, the accuracy might be a problem if the digital twin is not enough, let's say, synchronized, but those are things that we will be able to evaluate only when we have the whole system. But for sure, yes, the only way to compare, to understand the accuracy is to run the same decision in your digital twin and in the real twin, in the physical twin, and to see if you get to the same result, because that means that it's accurate, okay? Of course, there will be some approximation, because otherwise, I don't think it's predictable to have perfect performance. But typically, again, you will have the other modules to fill the gaps, so that it will be more difficult to take a wrong decision.
Any other question, please?
This diagram is all these blocks are inside a Mexico.
Inside?
All these blocks are inside a Mac center, 5G, the Mac centers, or the network topology, or I'm confused with the concept?
They are not necessarily, the thing is, this is the, let's say, it's sort of the business logic, if you want, of the system. So it can be in the data center of the provider, together with the core, but it can be also elsewhere. Because there is, the interaction with the infrastructure happens through the monitoring part and the orchestrator. Okay, so the 5G is here below. You have the core, the RAN, even not non-5G part. It can be Wi-Fi if you want on the end-to-end. If you can control it with an orchestrator, this can be applicable to all.
Okay, thank you.
You're welcome.
Any other question? So Fabrizio, thank
There's
you very
another
much.
one?
Oh, yes, please.
Yeah. I remember when I see some presentations about 5G, the part of network function virtualization. they use, for example, open source software.
Yeah.
I don't remember the name, but you work with some of them, or
Yes, we have. There is different. There is, for example, OpenAir interface is the one that EURECOM is producing. Is one reference software. Probably in the core, typically in my lab we use Open5GS, which is another open tool, and in this case, probably we will not, at least in the preliminary example, we will not have the real run, so we will use the UE Run Sim, which is a simulator for the run, because here we are interested more in how to configure, you know, the system, not much the run itself. So there are several open source software. The thing is, with open source software, you can do a lot. For example, to build the digital twin, probably we'll use those modules because they are lightweight, already containerized in Docker, so it's simple to arrange them. The problem is sometimes the performance, so you don't have maybe a realistic performance. In some cases, the latency especially is a crucial point that is not very well, let's say, modeled, but because it's not a commercial, it's not a optimized, let's say, software. And the thing is that not all the functionalities are present in the open source versions. For example, here we need to collect the data, and the network exposure function typically is not, I mean, if it's implemented, it's just a black block with nothing inside, so it's just there are interfaces, but they don't do anything. And also here we will need the NWDAF, that is one important network function that collects network data. So we need to implement some on some partners will do that, because we need some interfaces if we want to build it. So the limitation of open source is they are, of course, getting in line with the standards, but they require time to become. So they are good to make experiments, but not for. They are not complete at the moment.
question. That's about the 6G, what we need to talk about this digital 6G.
We will have, of course, during this is a 3 years project that we started this year, so we will not have 6G hardware because it will not exist. What we will do here, we will, I mean, we will use as a reference the 5G. So we will implement intelligence on 5G because. Yeah, it is. I mean, this approach is independent because you just need a way to collect data from the infrastructure on topology. So you need this kind of information. If you can do it with 5G, but you can do it with other, for example, with an SDN network, you can speak with the controller. There are several approaches. This project is focused on 6G because of some constraints on the security, you know, there are, but the work is general.
Yeah, but I think that the introduction of the intelligence, which what differs 6G from 5G, and I think what this digital twin is trying to do is how you canalize, how you apply the intelligence, machine learning, artificial intelligence, in the operation of the network. So it's said that in 6G, AI will be native, but how it will be there in the network. So I think that the title of the talk, that 6G from theory to practice, is exactly this, let's say, seminal moment that we are doing the transition from 5G to 6G, and introducing what is supposed to be different in 6G than we don't have in 5G.
Yeah.
I think this.
Yeah, it is. In fact, basically, we believe, I mean, in a lot of projects that are in this line, they study other aspects also. They all agree on the fact that the core of the network will be 5G evolved somehow, because from when 5G introduced the service-based architecture, the following releases are adding maybe functionalities, but the core is always, you know, the user playing function, this kind of structure. So we don't restrict ourselves too much in using the 5G because at the beginning 6G will build on top of that. Then maybe if it will not be able to satisfy all the requirements, probably it will have other, let's say, releases that will be more disruptive. But here, in most cases, not just this project, we believe that it will be an evolutionary process from 5G to 6G. So not exchange like, I don't know, between 2G and 3G. It will be an evolution, and a smooth evolution that will, the milestone will be network of autonomicity, IA, this kind of aspects.
One problem of the automation systems is to reach stable states. In the sense, for example, the system may decide to put one function and node A, and after the next cycle of collecting data to put in node B and node A and so on. Then my question about convergence with digital twins. Digital twins may turn easier to deal with convergence of the solutions.
That is a good question. Because on one side, on the stability, it's surely one of the issues. I don't think digital twin will directly solve that problem. My impression, but it's like a hot, let's say, right, real-time impression, I might think a little bit more, is that in the network, one of the problems is that, especially in a dynamic network like this one, the traffic itself will not be stable probably, because it will change, and that is why you need artificial intelligence. Otherwise, if everything is predictable, we close and we finish this. So probably the stability problem will be an issue also because of the state of the system, because the system itself will be unstable. I mean, not unstable in the sense to diverge, but dynamic in the sense that it will not be focused on one operating point. So maybe digital twin can, it might help to avoid some sort of oscillations, because what it can do is probably to test, it can be used to test if your strategy is stable, because you could say, tell me in 1 hour what would happen if I use this algorithm. So that is exactly what it can do. And you can see if you can ask in output an advice whether the network function will continuously move or ping-pong between two options. That yes.
Yes, because
but
it's
it
not
will not solve it
with a policy-based system.
No, exactly.
But with the AI, yes.
Yeah. I mean, if you ask whether the thing would be that the intent-based interface should make what-if scenarios that are very well prepared, if that is the objective. And I think that in that case it can help. It cannot tell you how to achieve stability, but it can tell you if that strategy under the current state would be stable. That yes.
Yeah, I think
Yeah,
that
There's another question.
yeah, maybe complementing the question, the answer for Fabrizio. Fabrizio mentioned reaching different point of stability. There is nothing to do with AI, but there is like a framework that is called what's the cost of flexibility? Exactly that if you make decision of changing the state, are you always willing to go to the optimal state, or do you want to pay the price of being non-optimal but achieve, let's say, a higher degree of stability? So these are the trade-offs, and it is basically which strategy you use when you have to make this change of state in the automation.
Yeah, in fact, in this, just also on this line, that here we are, it's not depicted here, but in general, the idea of the intent-based interface is also that the network manager can express intents. So it could say, I want to take only stable decisions, for example, in the intent. So the digital twin will tell you whether the situation is expected to be stable or not. It depends on how you express. But there is a man in the loop somehow, not in real time, because otherwise the whole system would take years. But the idea is that intent can come from services or from the network manager to say, I want this. And as Nelson was saying, maybe you can say, I prefer stability rather than maximum efficiency. Then it will tell you, okay, in this, based on these parameters, this seems to be better. Yes, please.
Sorry, it's just it's about the digital twins. I think just to complement the other questions. Probably it's a part of VNF inside of NFT concept. If you have something about network control, element control, probably going to be OSS matter. But for instance, for industry in general, do anything digital twin, you just allocate an VNF and probably you need to allocate resources on and the quality of service is probably not operating about stability.
I didn't understand exactly the question.
No, about
It's common.
no, it's about where to allocate this infrastructure
Okay.
inside the NFV concept. Probably inside of telecom network. Probably they will allocate a VNF you to build this, and they will provide to you resources and quality of service. If you have a problem with stability, they need to provide this.
Yeah, that is one. Here we didn't consider yet this how it will be deployed. We assume that it will be, let's say, the owner of these functionalities will be the mobile operator, because otherwise there are problems in managing the data, because I cannot have information about infrastructure from the outside. But we didn't yet, I mean, at this level we will implement it probably like web services or something simple. Then the real deployment, it will be the next step. But it might be with network functions. So it will be another burden on the data center of the provider.
Questions? A lot of questions.
Yeah, but it's nice. I like to discuss about those topics. So
Okay,
thanks for the
thanks
questions.
for the enlightening talk, for all the answers, bringing this topic to our institute, and for all discussion. Thank you.
My pleasure.